We're looking at the back page of the 7.2 worksheet, worksheet number 2. Find the volume of the solid whose base is bounded by y equals x plus 1. That's this graph here. Y equals x squared minus 1. That's the parabola. And we're looking for cross sections parallel to the y-axis that are different, various shapes. Hey, but let's first need to identify which direction that we're going to be drawing our base. Will it be top, bottom, or right minus left? So we want the cross sections to be parallel to the y-axis. So the y-axis is vertical. Parallel would also be vertical. So we want to draw a base that is vertical, so that we do top minus bottom. So the base for whatever shape that we want to build on top of this base, whether it's rectangles or equilateral triangles, we're going to be using this as a starting point. All right, so top minus bottom is going to be the linear minus the curve. So the linear is going to be x plus 1. The curve is going to be x squared minus 1. So x plus 1 minus parentheses x squared minus 1 will reduce to be negative x squared plus x plus 2. So this is the representative distance of this vertical base. And we're doing vertical bases from because this is top minus bottom, our bounds also have to be in terms of x. So if we use the calculator, we can find the intersection to be at -1 and at 2, or we could set the two equations equal to each other. We can set x plus 1 equal to x squared minus 1, and then solve for x, and we'll get -1 and 2. Now, for part A, we want rectangles that are of height 5. So let's think about the area first. The area of a rectangle is going to be base times height. The base is going to be this representation that we found, and the height will be a constant of 5. So base times height, the base we found that we're going to be using through for part A and B will be negative x squared plus x plus 2. The height is going to be 5. So to find the volume, we just are going to accumulate these infinite numbers of rectangles from -1 to 2 to build this three-dimensional object. All right, so the area is base times height, and then we take volume, we take the integral, definite integral from -1 to 2, which will accumulate all these infinite numbers of rectangles, and here we have the setup to find the volume. Okay, and the rest can be plugged in the calculator to find the actual volume. All right, we want for part B, we're trying to build equilateral triangles on top of this base. So the formula for equilateral triangles is √3/4 base squared. The base is what we found here, negative x squared plus x plus 2, quantity squared. So there should be a squared here. Negative x squared plus x plus 2 is quantity squared, √3/4, and then the bounds same from -1 to 2. Hey, number 5, find the volume of the solid whose base is bounded by x equals 0. So here's x equals 0. That's the vertical, that's y-axis. Y equals 0, that's the x-axis. 4/3 x minus 3, that's this linear graph here. And cross-sections, we're looking for cross-sections that are perpendicular to the x-axis. Sorry, to the y-axis. So y-axis is vertical, so perpendicular must be horizontal. So we now have a base that is horizontal, so we have to do right minus left. If we do right minus left, we have to rewrite our equation. This equation is a function in terms of x. We have to rewrite it as x equals a function in terms of y, or an equation in terms of y. So we have to solve for x. To solve for x, we can isolate the 4/3 x first, equals y plus 3, and then divide by 4/3, which is the same thing as multiplying by 3/4. So 3/4 y plus 9/4. So this is the equation that represents the right graph. The left graph is 0. So 3/4 y plus 9/4 minus 0 is going to be 3/4 y plus 9/4. So this is the representative base. And then the bound is going to be from the lowest y value to the highest y value, since everything's in terms of y. So lowest y value is -3. The highest y value of the shaded region is going to be 0. Okay. For A, we're trying to build semicircles on top of this base. So to do semicircles, the formula is pi over 8 base squared. The base is what we found here, so 3/4 y plus 9/4 squared. And but we want to accumulate these infinite numbers of semicircles from 1 one end to the other end. So from negative 3 to 3, sorry, negative 3 to 0. This is our volume formula. Okay, we're just doing the setup here. Okay, for part B, isosceles right triangle. So we're using the same base, but the formula is 1/4 base squared. So 1/4 parenthesis or bracket 3/4 y plus 9/4 squared, and then we're going to accumulate these infinite numbers of isosceles right triangles from one end to the other end. So from negative 3 to 0, 1/4, negative 3 to 0, definite integral of the base squared dy.